What's up? This is Mr. Rodriguez, and we are back with another video. Today, we are going to be going over rotational kinematics. So, really, this is going to be a review of kinematics the way you know it for linear kinematics, but we're going to be talking about the terminology and the variable names that we use for rotational kinematics. Now, mathematically, rotational kinematics works a lot like normal linear translational kinematics, but we just need to establish a few new terms. All right, if you notice here in this table, I have some translational terms next to their rotational terms. So in rotational kinematics, the terms on the right side of this table basically coincide with the translational linear terms that you see on the left side of the table. So instead of force, we're going to call it torque. Instead of mass, we're going to be talking about moment of inertia. Instead of acceleration, we're going to specify angular acceleration. Newton's second law, F equals ma, is typically written as torque equals moment of inertia times angular acceleration. Velocity v is now going to be replaced with angular velocity omega. And then for distance x or y, whatever variable you're using for distance, we're just pretty much going to be using angle theta for angular distance. Now, we're using a lot more Greek letters here, so let's go ahead and name them. That t that we're using for torque is actually the Greek letter tau. All right, that almost looks kind of like an X, kind of looks like a fish. That's alpha. We use that. That's the first letter in the Greek alphabet. That's going to be for angular acceleration. The letter that looks kind of like a W, but it's really it's really rounded, that's going to be the lowercase omega in the Greek alphabet. We're going to use that for angular velocity. And then, of course, you've seen it before, but we're also going to be using a lowercase theta for angular distance. So let's get into this and see how all of this works by defining angular distance. Basically, angular distance is how far you are moving around a circle or rotating about the center of a circle. So let's say that you are this purple box and you're moving in this direction around the circle, as you could see that I'm trying to kind of show you with these two images. This box is changing its angular position. Now, it could be going in circles forever and ever and ever, but it's continuing to change its angular distance, okay? Its angular distance is a matter of how far around this circle it's going, okay? So typically, this is going to be measured in degrees or it will be measured in radians. All right, so just as a reminder, there are 360 degrees in one revolution of a circle, and there are also 2 pi radians in one revolution of a circle. Again, regarding motion around a circle, 1 time gives you 2 pi radians or 360 degrees. If necessary, physical distance traveled around the circle, which we'll call arc length s, okay, when we're talking about physical distance around a circle, we usually use lowercase s. We'll call that arc length, and that can be related to angular distance in the following manner. So we'll have this relationship here. Your angular distance is equal to your physical distance around the circle divided by the radius of the circle. All right, so that means also, in other words, S is really just equal to theta, your angular distance, times the radius. All right, so let's start talking about what is angular velocity. Well, angular velocity, which we use as omega, it is a vector. And just like how linear velocity was defined as change in physical displacement or change in linear displacement over change in time, we're also going to be using the same kind of relationship, just with change in angular displacement over change in time. So that's going to be, sometimes it can be degrees over time, sometimes it can be revolutions over time, sometimes it can be radians over time. I think more likely you'll see radians over time when we're doing angular problems or rotational motion problems. But basically, in words, the definition is angular velocity equals change in angular displacement divided by change in time. So if ever you need to relate angular velocity back to linear velocity, then the relationship is similar to the linear position and angular position. It's going to be v is equal to the radius times angular velocity. So linear velocity is equal to radius of your circle times angular velocity. Now, of course, angular velocity has a direction because it's a vector. So let's actually talk about that, because it may not be exactly the way you think. We use actually a third dimension when we're talking about the direction of angular velocity, because there's not a way of actually expressing the definition in the two-dimensional plane. So we use what's called the right-hand rule to distinguish the direction of angular velocity when it's going clockwise versus when it's going counterclockwise. And the way that that right-hand rule is going to work is if you have some object or some kind of circular object that's going around in circular motion, okay? If the circular motion is counterclockwise, okay, then what you're going to do is you're going to take your right hand and you're going to curl your fingers around the direction of the motion that you're looking at, right? And so for this left hand figure here where the car is traveling in a circle around the circle here, if I were to curl my fingers of my right hand in the direction of the car's motion and stick my thumb out, my thumb will actually be it'll be pointing toward me out of the page. And so we say the direction of the angular velocity here is out of the page, and we actually show that by this figure here. It's like a little circle with a dot. That's suggesting that we have counterclockwise angular velocity, and so we're going to say that its direction is out of the page. Now, if the direction of the angular velocity is clockwise, and we still use our right hand to curl our fingers around that motion, then what's going to happen is our thumb is going to be pointing down into the screen away from us. So here we'd say that the angular velocity is into the page, and the way that we show that is with a little X inside of a circle. Now let's talk about angular acceleration. Angular acceleration works, again, just like normal linear acceleration, because where linear acceleration looks like this, a is equal to change in v over change in t. Instead of using linear velocity, we're just going to be using angular velocity, all right? And the units here are generally going to be radians over seconds squared or degrees over seconds squared. If you ever need to relate the angular acceleration back to linear acceleration, then you probably could have guessed a relationship. It's very similar to velocity and position. Linear acceleration is equal to the radius of the circle we're dealing with times angular acceleration. So let's talk about those constant acceleration situations, all right? So you know from kinematics that there are a whole slew of equations that you can use specifically for when acceleration is constant. And you'll see them here. And with my students, I call them the big five, even though some of them are kind of just variations of each other. There are rotational kinematic equations that are basically the exact same thing, and I have them next to each other here. You'll see that they're basically the exact same 5 equations that you can use for situations in which you're observing constant angular acceleration. The only thing is that we're using the angular versions of motion, like angular distance, angular velocity, angular acceleration. Time is still the same as usual, but nothing really ever changes there with time. All right, so notice that angular position replaces pretty much everywhere where there's an x, which was just, linear position. Omega replaces everywhere where there was a v, and then your alpha replaces anything that there was an a. And so the mathematics work exactly the same. They work exactly the same. So you can feel comfortable using the same mathematics. And for that matter, when you're actually doing graphical analysis of relationships in motion that are related to these equations, those graphs are going to look exactly the same. So you're still going to have things like area under curves equal the same things as they did in linear motion. It'll all work the same way with rotational motion. All right, let's work an example here. 4 children climb on a carousel that was initially at rest. If the carousel accelerates to 0.4 radians per second within 10 seconds, what is the angular acceleration? What is its linear acceleration? 3 meters from the axis of rotation. Okay, so if we can very easily find the angular acceleration here, okay, but if we want to know the linear acceleration, how it relates, then we need to know the radius of the circle that we're traveling. So it's good. It gave us the radius of the circle of 3 meters, okay? That said, let's go ahead and work this out. We have, of course, a change in, an acceleration such that we have a change in angular velocity of 0.4 radians per second. So we're looking for the angular acceleration. So I'm going to say alpha is equal to change in angular velocity over change in time. All right. And then I can calculate my change in angular velocity from my final angular velocity, which is 0.4 radians per second, minus my initial angular velocity, and it says that it started at rest, so I'm going to say 0 radians per second, over a time period of 10 seconds. So that just turns into 0.4 radians per second over 10 seconds. Let me make sure I carry my units here. That's 10 seconds, All right, so 0.4 divided by 10, we're just going to move that decimal place over one time. It's going to be 0.04 radians per second squared. So that's going to be my acceleration. That's 0.4 radians per second squared that we have over here on the right side of the screen. And if we want to actually bring that back to, well, how much is the carousel accelerating linearly? Like if we put a piece of tape at the edge of the carousel, how much is that piece of tape accelerating as that carousel starts to accelerate angularly? Well, that's not too hard as long as we know what the radius of the carousel is. All right, if we say that the radius of the carousel is 3 meters, then we can just relate this back like this. Linear acceleration is equal to the radius times the angular acceleration. So we're going to take that angular acceleration and just multiply it by the radius. So in this case, it's going to look like this. 3 meters times 0.04 radians per second squared. That will bring us to, let's see, 0.04 times 3. That should bring us to 0.12. And if you follow this relationship, you'll end back up with meters per second. All right. So we're going to, the end of that carousel, or 3 meters from the center of that carousel, is going to experience an actual linear acceleration of 0.12 meters per second as that carousel accelerates. Let's move on and touch on centripetal acceleration. All right. So you may remember from our centripetal acceleration unit that it's found using v squared over r. Okay, we use that for centripetal acceleration, and we use that as well as we continue to find a centripetal force. But in this case, if we're dealing with values in angular, like in terms of the angular motion, then we have to remember that the angular velocity relates to linear velocity in this manner. V is equal to the radius times angular velocity. So if we take that relationship and plug it into our V for centripetal acceleration, then what we get is a relationship where we're squaring that omega time, that angular velocity times radius, and we're dividing it again by radius as per the original centripetal acceleration relationship. So then if we simplify that a little bit, we get a relationship for centripetal acceleration that's in terms of angular velocity. So centripetal acceleration is equal to angular velocity squared times the radius of your circle. All right, that's all we have for introducing the position, velocity, acceleration details of angular, in terms of angular motion, in terms of circular motion. So there's going to be some practice problems assigned here, some solution videos posted. Good luck studying. I'll see you guys in the next one.